Okay, fine. So, welcome you all today formally in second lecture of module number 3, that is DCAC bridges. So, in the last lecture, we discussed about the need of the bridges, DC bridges and the AC bridges. In DC bridge, primarily we use the Wheatstone bridge as a configuration. It's important. Why do we need it at early stage? What is the importance of the bridges to reject the noise or unwanted signal? And DC or AC bridges is also used to find out the unknown parameters or the elements like resistance, capacitance, inductances, change in resistances, change in inductance, change in capacitance. Okay? So relative values you are calculating, remember it. Okay, and because physically whatever signal information is available around you uh, in different forms in the nature, that is in absolute form, that is in abstract form, in other words you call, but the machinery or the technology which you use to interpret into the electrical form, the physical variable to convert in electrical form and analyze its stories, it, that is you do in the always in relative form. So in this series, in the last lecture, we discussed about the Wheatstone Bridge, and now today we are supposed to discuss it over the AC bridges. Okay, so under the head of the DC AC bridges, you can say that it is a AC bridges portion. Now we'll see. So the first bridge, the fundamental bridge. So under the head of AC bridges, that means now in the couple of lectures, we are going to discuss about the measurement of the unknown inductances and the measurement of unknown capacitances. Right? So as you might have already studied at the inter-science level or the school level, that the Maxwell bridges, which is a very popular one, or which is the, you can say that the foundation of the AC bridges, way back, decades back when it was introduced, and the Maxwell has introduced it. So based on this, the name bridge name is identified, recognized as the Maxwell's bridge, and Maxwell bridge is primarily used for the measurement of unknown inductances. Clear? So how we are going to measure these unknown inductances? So this unknown value of inductances you can measure by comparing it with the standard inductance. I am talking about Maxwell bridges. Right? So this assignment in the red color I have mentioned in the bottom of this particular slide. So it is for your assignment. Okay. So whatever your assignment number for the module number 3, for module number 3, it is the first assignment question. Clear? Question number 1. Just note it down. And I would also suggest you that after the completion of this particular module, you will be requiring to submit your assignment sheet. It doesn't matter whether before the midsem or ends. Once this lecture series is finished, that is the module number 3, you are required to submit your assignment sheets for the evaluation. How you will submit, I will let you know. Okay? So in the Maxwell inductances bridges, what happened, if I will show you the Maxwell inductance capacitance bridges, in this 4 bridge you see, say for example arm AB, AC, BD and CD. AB is exactly the same. In case of AC, where the known resistance is mentioned here, in place of the known resistance R2 and a variable resistance L2 is also there, standard variable resistance. Okay, so standard inductance is there. So whether you talk about standard resistance, standard inductance, standard capacitance, very few country across the world they can manufacture it with this so high degree of accuracy, and it's very costly, remember. Okay. So what you use in our day-to-day life, in commercial life, is the secondary type. So it's cheap. Okay. It's cost effective. But the standard resistances, inductance, capacitance, the calibration purpose. So it's very costly. Or in other words, you can say it's a pure, as good as very nearly pure. Okay. So a standard variable inductances is connected in series with this R2, and there is no capacitance, remember, unlike in this figure it is. That is your Maxwell inductance bridge. Okay, so I would give you this assignment that draw the circuit diagram of Maxwell inductance bridge and find out the equations, the mathematical model in the balancing condition. Apply the balancing condition. Find out the value of unknown inductance L1 in case of Maxwell inductance bridge. Okay, and also identify the limitations. So let me tell you the limitations. What happened in Maxwell inductance bridge, because there is no capacitance in that case. So because the two inductances are involved in the same circuit, now what problem will occur? Can anybody say? When more than one magnetic field exists in the same circuit or within the same environment, what will happen? There is a possible chances of mutual inductance, and this mutual inductance will give you the additional amount of inductance. Okay, maybe additive or maybe in subtractive form, maybe plus or minus, but it will give you additional amount of inductances. Okay, so in that case effective inductance will not be equal to the sum of the individual magnitude of the inductances. So this can change your accuracy of the measurement. So that's why it is very difficult. Number two, manufacturing a standard inductance is the most costliest process, most difficult process as compared to manufacturing a standard capacitor and the standard resistors. Remember this. Okay, so that's why to avoid those nullify those limitations, now we are going to discuss the Maxwell inductance capacitance bridge. So remember, Maxwell inductance capacitance bridge also known as sometimes as the modified Maxwell's bridges. Okay, modified Maxwell's inductance bridge is called modified bridge, or as per the nomenclature, it is called Maxwell inductance capacitance bridge. Okay. So now, unlike Maxwell inductance bridge, what we will do here, we are going to find out the unknown value of inductance, yes, but by comparing it with the standard variable capacitance, not the standard variable inductance. Yeah. So as I told you that you are going to measure the unknown value of inductance using the known value of standard variable capacitance in place of standard variable inductance, what is used in the initial design of the Maxwell inductance bridge. Okay, so now this is the modified circuit. So here you see in the first arm R1 is in connected with L1. So don't be confused. This R1 is not the additional amount of resistance in circuit. Okay, when you will construct the original bridge, only inductance is there, but what this R1 is indicating in that case, R1 is indicating the amount of resistance available in this inductance. Okay, because it is not a very pure inductance, it is not a standard inductance, it is an unknown value of inductance. So to represent the amount of heat loss or heat generation generated when the current will flow through the inductor due to the power loss, that amount of resistance, that amount of heat generation with respect to the power loss is indicated by the value of R. So this is the magnitude of R. Okay. So in some of the good books, it is also referred as small R1. That is shows the internal resistance. So R1 is here is nothing but it's like an internal resistance. It is not an external resistance. Be noted. Okay. Then R2 is your secondary resistance, which is known. R3 is also secondary resistance, which is known. R4 is a variable resistance, and in place of the standard variable inductance L2, here the circuit is modified by the Maxwell later on, and a variable capacitor, standard capacitor, is connected across the C and D in place of inductance in across A and C. So remember, it's complementary circuit. Okay, impact of inductance in series network will be the more or less similar in terms of frequency variation, I'm telling you, or in terms of Q factor and bandwidth, I'm telling you. Then whenever we apply, switching it with the capacitor but across the parallel to the resistor. Okay, so the series RL network is the complementary of series RC, parallel RC network. Here's a diagram. I hope that you will be able to get it. Did not to be explained. So this is the theory. We just later on manage it. Now I am assuming that you apply the balancing condition with the help of the null detector or the D Arsenal meter, galvanometer. And once you achieve the balancing condition, so that means the magnitude of the current which is passing through the AB bridge Okay, arm is equal to the same amount of current will pass through the VDR. Similarly, the amount of current passing through the AC arm will be remain same, I2, equal to the amount of current passing through the CDR. So in that case, when you will apply the balancing condition, this is the standard equation you got, because R1 is in series with the L1 in the arm 1, and in arm 4, R4 is in parallel with the C4. So you modified this equation. Now what will happen? You will get a real component and imaginary component. So just separately equate or compare the real component and separately compare the imaginary component. What you are getting? R1, which is the internal resistance of the inductance, L1, which is under the measurement, because remember, L1 is the unknown value of the inductance, okay, which you need to find out. So R1 is equal to R2 into R3 by R4, and L1 you are getting C4 into R2 R3. Done? Now, if you will see over here, in that case, you are not getting any frequency component. Okay, as you can see that whether you talk about the equation R1 is equal to R2 into R3 by R4, or whether you talk about L1 is equal to C4 into R2 into R3. Okay, in both the expressions you see the value of L1 and R1 do not depend on the supply frequency. Okay, do not depend on the supply frequency, and therefore you can say that this bridge configuration, like Maxwell inductance bridge also, okay, Maxwell inductance bridge also has the same advantage, but like the original Maxwell inductance bridge, in case of modified Maxwell inductance bridge or Maxwell inductance capacitance bridge, is also immune from the frequency variation. That means if there is a variation in supply frequency, okay, which is naturally occur in your day-to-day life, the measurement of the unknown value of inductance or the accuracy of the measurement of the unknown value of inductance using Maxwell inductance bridges is will remain unaffected. That is a very positive point. Okay, so accuracy of measurement will be good, and also because it is don't depend on the supply frequency, so that means it's easy to understand that your measurement will be also free from the even harmonic distortions as far as the power supply is concerned. Clear? So in this scenario, you would be say that uh, let us see what is the impact over the Q factor of the Maxwell bridges. So as I've been told you that why you are going to measure the Q factor. So basically Q factor is nothing but is the ratio of the reactive component upon the resistive component as far as any LC bridge is concerned, because here you are going to consider the impact over the resistance, because resistance is indicating the amount of uh, heat loss which occur due to the current flow or due to the power loss, you can say. Okay, so ideally you should have an inductor which has that have a zero resistance. Okay, zero resistance means there is a no heat loss, fine, or in other words there is a no power loss. Clear? So Q factor is indicating the quality of the inductor is used, that how the the inductor which is under the measurement, how close it is or to the ideal inductor, you can say, or the real inductors. Okay, so Q factor is primarily defines the ratio of inductance reactance with respect to its resistance at a given frequency, right? So that means ideally your Q factor should be very high or infinite, right? So if Q factor is infinite only if the R is tending to 0, that means the internal resistance of the inductor is offering zero resistance. Clear? Okay. So as far as this demonstration is concerned, how we can find out? Because your unknown value is L1, your internal resistance is R1. So from equation 6.11, if you will substitute my Q factor right now, is actually omega L1 by R1. Now you know the value of L1 and R1. L1 is equal to C4 R2 R3, and R1 is equal to R2 into R3 by R4, because remember right hand side is the known value. So you substitute this. So in that case, Q factor you are getting omega C4 R4. Now, what do you mean by that? That this relationship when the Q factor is equal to omega C4 R4, So it shows that the bridge is not much suitable for the measurement of the high Q factor, because for the high Q factor, remember that your supply frequency is ideally should be constant. है ना? Your omega of the circuitry is should be constant. C4 should is an element, the value is constant. So what else you have? Variable resistance. So what you need to do that to increase the value of Q factor, which is ideally we should achieve, you need a very high capacity resistance, which is impractical to apply, because if you are going to increase the size of resistance, your measuring device size, your measurement device size, that means the bridge size, because this bridge you are going to use the measurement for measurement of unknown inductance. So your size is going to be increased. It is going to be very bulky, okay, and impractical for the transportation purpose when you particularly talk about the field measurement in the plant-like environment. Okay? So is not suitable. So you can say that Maxwell bridges is primarily, theoretically it is suitable for any value between less than, for greater than 1 and less than 10. Okay. So normally Q factor, Maxwell bridges are used for measuring any value of Q factor. Q factor is a parameter that is between 1 to 10, more than 1 but less than 10. Clear? It is also not very suitable for measuring the very low factor of the low value of the Q factor, less than 1 particularly. Okay. So we will see that thing later on. And okay, other than that, as I've been told you that the even in case of inductance capacitance bridge, you require a standard variable capacitor. Okay, obviously it is far easier because the capacitor is depends operates on electrostatic effect rather than the yes, rather than the influence by the electric field rather than the magnetic field. Okay, which is more difficult to handle, but still the standard capacitors are very expensive. Okay, in some of the state of the art laboratories and the research labs in India, in various places you can see those things. Okay, so in such a case, uh, what we happen then we use a fixed value of capacitor, okay, rather than standard capacitor, and then we try to neutralize the impact using by varying the value of R2, okay, and the by choosing a different value of R2 and the by varying the value of R4. So remember, R4 is basically a variable resistance you have. Okay, so that is the one point. As I've been already told you that Maxwell bridge is also not suitable for measuring the very low value of Q factor. Okay, so in that case, what will happen when you will go for the inductive resistors or RF coils, radio frequency coils, like in many communication based applications or RF radio frequency applications. Okay, in that case, those frequencies can be interlaced or interfere with your original measuring signal. So it will become your signal to noise ratio very poor and will give you very poor results. Okay. Now, to overcome from that particular situation, particularly the high Q factor limitation, okay, because it is not recommended to use Maxwell bridge for the measurement of Q factor more than 10. Less than, it is always recommended for less than 10, even not equal to 10. Hayes has modified as this particular Maxwell bridge itself, okay, after the decades of time, and then he introduced a new combination. So as you can see here, this R1 is still internal resistance, so RAB is remains same, RBD is remains same, RAD is also remains same. What it does, it replaces that capacitor which is applied in parallel to the R4 in case of Maxwell some modified bridge or Maxwell inductance capacitance bridge. Here it is connected in series. Remember, okay? So in Hayes bridge, it is connected in series. Okay, so accordingly, remember in the right hand side, as you see the phasor diagram demonstration, it will definitely change. Clear? I hope you will be able to appreciate it. Now at the balancing condition, I try to write down that equation, standard equation, right? So that Z1 upon Z3 is equal to Z2 upon Z4. So as per this demonstration, so you apply this particular the value of Z1, Z2, Z3, Z4, and separate the real part, separate the imaginary part. So you got the two equations in terms of the real value and the imaginary values. Okay. Now in both the equations, whether you talk about the real part or whether you talk about the imaginary part, Okay, what is your ultimate goal? Your ultimate goal is to find out the value of L1. Clear? So we have the unknown quantities. So if you will substitute these values of L1, because um, because what you can do, that you can replace these values in such a way that it can offer you the minimum amount of variables, because right now in the upper equation you see, to find out the value of L1, unknown value of inductance, you required 1 2 3 4 5 different known values, okay, with good accuracy. In the secondary equation, in imaginary form of equation, you require the value of omega as well as the remaining three, that is R1, R4 and C4. Okay. So in that case, if you see that by substituting these values over each other, you can get the value of L1 and R1 in this particular form. Okay. Remember, your Q factor is 1 upon omega RC. Yeah. So if you will substitute these values, because in the balancing condition you can achieve this balancing condition in terms of the inductances RL circuit only. Okay, in that case it is omega L by R, or using the LC circuit reform, that is your 1 upon omega LC. Okay, so if you will substitute, whether you adopt omega L by R, so it is omega L1 by R1. If you will adopt 1 upon omega RC, then in that case 1 upon omega RC, what will happen? You will substitute this value because it is omega L1 R4. Okay, so modified in this form, that it should be rearranged in the form of RC. So RC, it is your C4 R4 you are getting. Yeah, because the omega square become negative. So you substitute those values. So here you will see that if you refer the equation number 6.17 at the balancing condition, okay, it shows that by the Hayes bridge combination will be able to measure higher, it will not only able to measure the unknown value of inductance, but it can offer you this measurement with accuracy for any higher value of the Q factor. Okay, because now if you are going to reduce, okay, what you need a higher value of capacitor, you need a very small amount of C4, and lower the value of C4, it is good for the circuit. Okay. Number two, can attain by varying the value of R2 only. Okay, without losing much accuracy. So in these kind of networks, what will happen? By only varying the value of R2, which is the already known to you. If you see the original circuit, this is R2. By the value varying the value of R2, you can attain the very high value of the very high accuracy. Now you know the value of L1 is given over here. If I will substitute the equation over here, if Q is equal to 1 upon omega R4 C4, so you substitute over here, this equation will be modified as L1 is equal to R2 R3 C4 upon 1 plus 1 upon Q square. Right? Now if the Q is kept on increasing, what will happen? This denominator is tending to 1. Right, or in other words, L1 is nearly equal to R2 R3 C4. Now you see that if L1 is equal to R2 R3 C4, when the unknown value of L1 is same, it is exactly nearly same what you have essentially achieved in case of the modified Maxwell bridges also, as you can see over here. Clear? You see it is C4 R2 R3 L1, and here also you are getting the same thing, that is L1 is equal to C4 R2 R3. That means the measurement of the unknown value of inductance is remain unaffected in case of the Hayes bridge, which is again further modified Maxwell bridge, you can say. Okay, Maxwell's modified Maxwell inductance capacitance bridge, but also it offers you the higher value of Q. So these are the two advantages you will get in case of the modified Hayes bridge. Okay, so I hope that makes sense to you. Now let us see the one more bridge. Now Ohms has introduced a different combination over here, and as you can see that this bridge is used for the measurement of unknown inductance. Okay, in terms of the known value of the capacitance. Yeah. So what it has been done in terms of circuitry, we will straight away refer, and you will get the idea that how different it is. Now you can see, appreciate. Okay, so this particular circuit, remember I have referred from the different books, so don't be confused about the figure now. Okay, and that's why the circuit representation is also little different. Yeah. So now you see in case of Ohm's bridge, remember L1 comma R1 is shown. So there is two ways to show. You can apply a series resistance through the inductance L1, that is also correct, or you can write it in this way also, where R1 is comma R1 is showing is nothing but it is the internal resistance offered by the inductance L1 which is under the measurement. R3 is remains same. C4 is now, remember, it is not a variable capacitor, it is a fixed capacitor. Okay, and R2 and C2 are considered as a variable resistance and variable capacitance in the arm number 2. Okay, in other words, arm number A between A and C. Yeah. So accordingly, you do the phasor diagram representation. I hope that there you should not feel any difficulty. Apply the balancing condition. So in that case, what happened? R1 plus j omega L1, okay, multiplied by 1 upon j omega C4 should be equal to R2 into, okay, R3 into this R2 in series with the C2. Clear? So if you will apply the right away straight away this equation, so that is how you are getting. Yeah, R2 plus your XC is equal to 1 upon j omega C2. So substitute these values, simplify the real and imaginary part. As you can see, appreciate that R1 is equal to the internal resistance of the unknown value of the inductance is equal to R3 into C4 by C2, whereas L1 is equal to C4 into R2 R3. So it is again exactly the same expression what you got in the Maxwell inductance bridge and in the Hayes bridge also. Okay, on the other hand, that the value of R2 is the ratio of R3 upon C4 C2 because it is the ratio of capacitances. So remember, again it is free from the any frequency variation. Okay, so that's how in this way the two independent variables, the C2 and the R2, are used for obtaining the balance condition, and the balance condition equation as shown in these two statement is very simple. Okay, as you see, the amount of mathematics you are required to solve in case of the Maxwell inductance capacitance bridge and in the Hayes bridge. So in Owen's bridge, it directly shows that this combination offer you very simple mathematical expressions. So what does it means? If the mathematical expression is simple, if you are required lesser amount of steps to solve it, the mathematical expression, so that means your measurement will become fast. Okay, and the simple also. So that means the construction of the bridge will be simple. That means it will be cost effective. Okay, okay. So but what happened? Remember that you are using one variable capacitor, so it will definitely offer a little more price, but not as like you have used the standard capacitors in case of the and standard inductors in case of the Maxwell inductance bridge and Maxwell inductance. Obviously, the Owen's bridge is much cost effective as compared to Maxwell bridge at least. Okay. So in Hayes bridge, obviously the advantage you are getting higher Q factor, but the mathematics is very complicated. And in case of the Owen's bridge, the construction is very simple. Mathematically, for evaluation is very simple, and it is also free from the frequency variations. Clear? So that is the advantage you are getting in case of the Owen's bridge, and that is the end of the measurement of the inductance, unknown value of inductance in the today's class. Okay. I would suggest you that we have a couple of amount of minutes of time. Uh, Note down these two problems, I would say, and uh, then try to solve it. Okay, you have a couple of minutes. Okay, so try to solve this problem here itself. The circuitry is given. Remember, in examination, the circuitry may not be given. Do not expect. Okay, so Maxwell inductance capacitance bridge is used to measure unknown value of inductance. The bridge constant at the bridge balance pure resistance arm is equal to 2.5 kilo ohm and the 50 ohm. So that means the value of R2 and R3 we are talking about. Okay, and the third arm has a capacitance, the value of your third arm means in this problem it is third arm, but as per our theory it is our fourth arm. Okay, so it's up to you, whatever you want to way to see. Okay, so it is 0.012 microfarad in series with a resistor of 235 kilo ohm. Okay, find the series equivalent value of the impedances. That is one problem. So just note down this problem. Try to exercise a little later. Not a problem. I'll give you a couple of minutes of time. Just note down this problem. If you wish to solve it, you solve it. Okay, take the next problem. The four arm of a bridge are connected as follows. Arm AB. You can connect AB, BC, CD, CA, DA in any form. Okay, you can choose the arm position. It is not necessary that always you take one. Okay, so arm AB is basically a choke coil L1 with the equivalent series resistance R1, which is under the measurement. BC is a non-inductive resistance. That means it is a fixed resistance R3. It is assumed. R4 is a mica capacitor C4. Okay, and which is connected in series with the R4, and a non-inductive resistance is given in your R2. Okay, so I hope that you can guess. Okay, can anybody say? It is nothing but just we have seen the Owen's resistance, Owen's bridge here. Okay, so no, is the one Hayes bridge, I think. Yes, it's a Hayes bridge. So draw a Hayes bridge, and as per this configuration, okay, identify the bridge, draw the Hayes bridge, and calculate the resistance and impedance of the chain coil. That is the value of R1 and R2. Substitute the equations, and in the Hayes bridge, I would recommend that in the descriptive problem for competitive exam like GATE and so, fine, it is no harm to remember it. But from the descriptive point of view, the steps is always very important. So apply the balancing condition, write down the equation, solve it, separate the real and imaginary part, and then you find out the unknown value of R. So you must get around 0.43 Henry, and the internal resistance is 57.8. So that is nearly around 60 ohm. You can say. So that is the end of the today's lecture. So with this, we are going to stop the recording. So with this, we are going to meet for the next time. Okay. And in next class, we are going to supposed to discuss the measurement of unknown value of capacitance. Okay. So till then, if you have any question, fine. Otherwise, you can depart. Any questions? Fine. No question, then you can depart. Arman, if you are present, or Shirabdi, anyone, just extend the list of absentees. Finally, okay, you can consider 42 participants. Rest of the absentees, you just WhatsApp me. Okay, mention in chat box. Thank you, Arman. Arman, better is that you just WhatsApp me. Okay, within 2 minutes, probably the session will be closed. So, or you go and just take a snapshot. Okay, no need. Okay, I'll note it down here itself. Arman, just for one information, 3 students are not here. So just remove those names. Did not require to mention again and again. Thank you.